All right, here we go. Unit 1, Day 3, Analytical Limits. Today we're going to evaluate limits analytically, including direct substitution, cancellation, and rationalization. What that term analytically means in our class typically is that we're going to be doing some kind of analysis without a visual aid. So we're not going to be looking at graphs anymore when evaluating limits. We will for a while so you can see the parallels, but the idea today is that we're going to take the same limit analysis skills that we've developed and start to do them just when given the function and without a picture. The first key to this is that if a function is continuous, okay, a continuous function, layman's terms, right? If you can drag your pencil across the function to draw it without lifting your pencil, it's a continuous function. It means it has no holes, no breaks, no jumps, no vertical asymptotes. If that's true, if it's a normal continuous function, then the limit as x approaches some value of that function is the same thing as what you get when you evaluate the function when you just simply plug in. And so we'll first just look at that in a picture. So this is the function 1/2 x squared minus 2x plus 3. If I just gave you the graph and I said, what's the limit as x approaches 3? We'd look on our graph at what's going on when x is 3, the limit from the left, the limit from the right, and we'd go over and we'd easily see that this limit was 1.5, 1.5. Now it turns out though that because this is a continuous function, that is the exact same thing as f of 3. So all you had to do here was to do 1/2 3 squared minus 2 times 3 plus 3, right? And you work that math out, you've got 3 squared is 9, half of that, you got 4.5 minus 6 plus 3. You get there that is 1.5. So that is the limit of f of x as x approaches 3. And you could have gotten that just by what we call direct substitution or plugging in. That works for any kind of continuous function. So all polynomials are continuous functions. All of our sine and cosine graphs are continuous functions. So if we wanted to find the limit as x approaches pi over 2 of the sine of 2 theta, all we would have to do is plug in the sine of 2 times, we plug in our theta, we plug in our pi over 2. Yep, here it is, unit circle. Told you it would come up. And so we have the sine of pi. I'm going to give you a unit circle reference. It's something that you want to start off by just memorizing the cardinal directions, but you're going to get there. For now, you can just look it up when you need it. Here's just a quick sketch of our unit circle. We're going to have 0, pi over 2, and then pi. So we're right here on our unit circle, halfway around. Circumference is 2 pi. And the sine of pi, sine is our vertical orientation there. So we've got the y-coordinate is 0. So this limit is 0, just like you would see on the graph. The limit from the left, the limit from the right, and in this case, because it's a continuous function, the actual value itself are all 0. One last one, little error here. This should say log base 8. The limit as x approaches 9 of the log base 8 of 11 minus x. And so we're going to plug in. We would have the log base 8 of 2. Remember how logs work? This is just asking what power of 8 is 2, right? This is asking 8 to what power equals 2. And in this case, this is going to be 1/3. Because remember, our fractional exponents, 8 to the 1/3 would be the cube root of 8. What times itself 3 times is 8? That's 2. That's why the log base 8 of 2 is 1/3. And just to check on our graph before we put it in, if we look when x is 9, yep, there it is. From the left, from the right, and in this case, because we have a continuous function, the actual value is 1/3. So anytime you have a continuous function, anytime you don't have any discontinuities, you never end up dividing by 0, you never end up taking the square root of a negative number, you don't have to worry about that. You can just plug right in, that's your limit. Here's a non-example, and this is what we're going to be spending most of our time on today. Let's say we went ahead and tried to plug in -3 to find this limit. So we always try direct substitution first, because if it works, you're done. get to go home, plus 3 over negative 3 squared plus 2 times negative 3 minus 3. So on top here, we'll have 9 minus 12 plus 3. That's 0. On the bottom, we'll have 9 minus 6 minus 3. We will also have 0. Now, 0 over 0 is not the same thing as 0. You cannot just divide by 0. This actually just means our function is undefined at this point. You put a negative 3 in the magic box that this function represents, nothing comes out. We cannot evaluate this function at negative 3. However, that does not mean the limit does not exist at that point. And you've already developed an intuition for this graphically. Here is the graph of this same function. This is something I could have given you on Delta Math last week. If I asked you what the limit is as x approaches negative 3, you'd look at the limit from the left, you'd look at the limit from the right, you'd note the discontinuity, but it doesn't matter. As we are getting closer and closer and closer from the left and from the right to our x coordinate being 3, our y coordinate is approaching 1/2. It does not matter that there is a discontinuity here. We know that the limit, the y value we're getting closer and closer and closer to, is 1/2. Next, the limit as x approaches 1 from the left. I always make a little note to myself, from the left and from the right. As we approach 1 from the left, well, we're going down towards negative infinity. We learned that this is negative infinity. Depending on your textbook, you can also call that does not exist. Versus if we approach 1 from the right, we're coming from the right-hand side, we're going up to positive infinity. So the question is, if we didn't get to see the graph, how could we come to those same conclusions analytically, right? Without a graph, analytically. And it turns out it's pretty much the exact same thing that you were used to doing in pre-cal to analyze whether something had a removable discontinuity or a non-removable discontinuity. Same steps. The first thing we're going to do is factor. So I'm going to rewrite my limit statement. It's the limit as x approaches negative 3 of factoring x plus 3. You'll get a lot of factoring practice. X plus 1 over x squared plus 2x minus 3. That's going to be x minus, let's do this first, x plus 3 times x minus 1 when we factor, so we get the plus 2x in the middle. So you'll notice what happens, right? So let me just kind of walk back to what this would look like in pre-cal. What you'd be asked to do is you'd say, okay, what kind of discontinuity is it? Well, the problem was if we plugged in negative 3, we ended up dividing by 0. Because we can get rid of it, we can remove that factor. This is a removable discontinuity. This is that whole. And so what we have here now is we finish off by doing direct substitution again. We just do direct substitution with what's left. So this is going to be equal to negative 3 plus 1 over negative 3 minus 1. This is going to be negative 2 over negative 4, like we got when we looked at the graph. This is 1/2. So that's how you do it analytically. You remove the discontinuity if you can. Now, if you can't remove the discontinuity, right? So remember here, same idea, it's the same exact function. When we factor, we're going to get this simplified fraction. We're going to have x plus 1 over x minus 1, right? This is the same thing that's right there. All we need to really test is to see, okay, I know this is non-removable, so I know it's a vertical asymptote. Am I heading towards negative infinity or positive infinity? And all you got to do, just try a point to the left. That'll tell you what's happening as you approach from the left. Find a point to the right. That'll tell you what's happening as we approach from the right. So let's pretend we plugged in 0.9, right? So we've got our vertical asymptote. Draw that a little nicer. We've got our vertical asymptote. It's at 1. We're basically just going to test what happens slightly to the left of that number. So we plug in 0.9. We'd have 0.9 plus 1. We'd have 1.9 over 0.9 minus 1. Well, that's negative 0.1. This is a negative number. So you started at your vertical asymptote. You just checked directly to the left, and it was already a negative number. So I can tell here that this means my function is going to negative infinity. We're going to negative infinity on that side. Versus if I plug in something to the right of the asymptote, if I plug in 1.1 to the right of it, I would have 2.1 over 1.1 minus 1 minus 0.1. And so this would be a positive number. This means that this limit we are approaching positive infinity. So that's how you would analyze the asymptotes here. Again, something that I'm pretty sure you've gotten at least close to doing in pre-cal. Last couple things for today. This is on the rarer side, but it does happen. Sometimes you can put your function into an alternate form through what we call rationalization. So you can remove these radicals or turn them around in order to get rid of what was causing your discontinuity. In this case, you can see we have a discontinuity at 3, and we can see the reason for that is that we have a division by 3 here. Or a division by 0 when we plug in 3. So what we're going to do is we're going to take this function, the square root of x plus 1 minus 2 all over x minus 3, and we're going to multiply by the conjugate. We are going to multiply by the square root of x plus 1 plus 2 over the square root of x plus 1 plus 2. Kind of weird, right? We're allowed to do it because it's just the same thing as 1, so there's no reason we wouldn't be allowed to do that. And the idea here is just that sometimes if you try out these different manipulations of functions, you get rid of the discontinuity that you had. In this case, the square root of x plus 1, remember these are going to be like binomial multiplications. The square root of x plus 1 times the square root of x plus 1, that's just x plus 1. The middle terms are going to cancel out, right? So you'll have, we already did this. Now we'll do x plus 1, the square root of x plus 1 times 2, and then you'll have times a negative 2, and the negative and positive 2's will cancel out. Then you'll have negative 2 times positive 2. This is going to be minus 4. So I think you can start to see why this is going to be helpful here, is that we're going to have some things that cancel out. In the denominator, we're going to have x minus 3, and you'll see why I do this in a second, x minus 3 times the square root of x plus 1 plus 2. Now this may look weird. Why did I multiply the top one out but not the bottom one? Well, it turns out I did that because if you do x plus 1 minus 4, that's just x minus 3. So what's going to happen here is your x minus 3's are going to cancel, and what you're going to be left with is just the square root of x plus 1 plus 2 on the bottom. So this will cancel, and what you'll have here, I know this is getting really weird, but this is equal to the limit as x approaches 3 of 1 over, right, there's nothing left on the numerator, it doesn't become 0, it becomes 1 over the square root of x plus 1 plus 2, that's equal to 1 over the square root of 4 plus 2, that's 1 over 2 plus 2, that is going to be 1/4. So 1/4 there. That is by far, like I would say, the least common one, but do be aware that it is something that you might want to try if all else fails. Finally, the last piece for today is just to get the idea of what it would mean to look at a limit of a piecewise function. So as you can see in this graph here, we've got two functions. We've got the red function, which applies everywhere up to -2 from the left, and then the blue function takes over from -2 on. So that's a piecewise function. Two functions. We have a dividing line here where if x is less than -2, we're following the red line. If x is right of -2, we're following the blue line. If I asked you to find the limit as x approaches -2, wouldn't be a problem here. Yes, we've got that kink in the graph, but that doesn't matter. The limit would be 2. You can do the same thing if you are given the piecewise function in this form. The key thing is just to remember that x is less than -2. There's your from the left. And the x is greater than -2. There's your from the right. So if we want to see if the overall limit exists, We plug into the upper part of the piecewise function, the 2x squared plus 3x, to find what the limit is from the left, and we plug into 1/2 x plus 1 to find out what's happening from the right. In this case, if we plug in, this says as x approaches -2 from the left, so we're going to have 2 times -2 squared plus 3 times -2, 2 times 4 minus 6, so that's going to be equal to 2. From the right, we will use the bottom function, -1/2 times -2 plus 1. We're going to have 1 plus 1. We get 2. The limit from the right is 2. The limit from the left is 2. Just like we would find on the graph, the overall limit is 2. So what I want to hit home today is just a last key point here, is that when we are analyzing limits, it's basically a flow chart, right? The flow chart begins, you always want to try direct substitution. If direct substitution works, then you're done. If you have a continuous function and you can plug in and you get an answer out, you're done. That's the limit. If direct substitution doesn't work, then you can do a few different things, and we'll learn more, but right now we only know 2. We know to factor, cancel, and do direct substitution again, and we know to rationalize. So we're going to try those toolkits out in our practice today.